Hello guys, hope you had a nice holiday with the Easter. So back to the lecture series. So this lecture will we will talk about recycling of zinc, and we have already covered recycling of steel and lead, and with zinc and copper we are ending all the metal series. So thus far, I think I have introduced you in every lecture both the traditional methods of recycling as well as we have talked about the chemistries behind recycling. I have gone a little bit of a diverted route into talking about fundamentals behind recycling, which is technically on the metallurgical side. And with copper, we will be finishing off with all the metals. And then there will be one more lecture on generic V, waste electrical and electronics, and how things are processed. And once that is done, we are almost completely done. At which point I want to do, let's say, some sort of puzzles and challenges in recycling. And at the end of this lecture, I will give brief introduction into what I want to do and what I have in mind. I think it's quite exciting to do courses this way, but let's see how it goes. So what will we cover in this lecture? I'll give a brief introduction into the primary production of zinc, okay? Because I think it's important to know the traditional way zinc is produced. We also have two types of processes, both pyro and hydrometallurgical processes for zinc primary production. I'll just give a brief introduction into the hydrometallurgical process because that is really the dominant process. More than 80% of zinc I think is produced from hydro. Pyro, I think it's yeah, there is 20% of production, but it's not a lot. But zinc recycling is quite exciting and complicated topic because I think the fact is that zinc is such a dynamic metal, which means it's used in a lot of applications, which showcasts its ability to be a functional material in many products, which is good, but also it showcasts the difficulty in how it's really difficult to recycle zinc. I think right now we have 30% of end of EOLRR, in all honesty, because yeah, you'll see numbers going up to 45, 40 with very specific European or US context. Okay, but overall in the world, the EOLRR is quite low for zinc, and that is because of the diversity of applications. Because you see, when it comes to lead, we saw lead, which is also a very interesting case scenario. In lead, we have a very high EOLRR. That is primarily because it's exclusively used in one type of application, so it's easy to design processes for them. Here, there are ways to recycle zinc, of course, but you can't throw every type of waste into that reactor and then expect a result. That is the key bottleneck of zinc recycling, in my opinion. And we will talk briefly about zinc recycling. I'll give you an overview about zinc oxide production from the dross, which is basically from the galvanic galvanization process. So we have two different furnaces to deal with it. The chemistry is pretty similar, only a little bit of tweaking with regards to two different furnaces. Then we will go to the electric arc furnace dust. You already know a lot about EAF because I have given you the lecture on EAF. So EAF dust is also a really important source for recycling zinc, and traditionally the Wahl's kilns or the Wahl's process is the really famous process for zinc recycling from EAF dust. But also already a lot of hydrometallurgical plants exist to process EAF dust. We'll go not on a plant level, but we'll go a little bit into a finer chemistry of how it is done. And I'll give you some variations, some really interesting concepts over there, which is super interesting. So we'll touch upon a few things there. And then the rest is pretty much miscellaneous stuff because yeah, you have so many sources actually. It's impossible for me to cover in this lecture because there are so many directions we can go. We will touch upon a few things, but I can never be complete with zinc recycling because there is such a lot of variety of gamut of sources. and we will touch upon only a few things in this lecture. Okay, before we go to the figure in the left, it's good to see the figure in the right because it showcases sort of the various types of applications for zinc. The primary major application is of course galvanizing. So I think you might have already heard about hot dip galvanizing. So people usually coat these zinc onto the steel or iron to prevent corrosion. And I have an interesting question for you to figure out yourself. Do you know why they coat zinc and why not something else? Why not cobalt, nickel, some other metal? Do you know why they coat zinc? If you should know why, because we already talked about it a little bit in the electrochemical series and whatnot. So we have also brass and bronze. Of course, it's an important application, but so many different, I mean, like it says here zinc alloys, others and zinc compounds. Of course, like we have applications in pharmaceuticals, we have applications in pigments, we have applications even in like solar cells, batteries, and so many other places. So it's really varied, and that really takes us to the figure in the left, where you could see that almost out of 16 million tons of zinc produced per year, 12 million tons comes from primary production. So when they say mined zinc in 1 year, it simply means primary production, right? So we have 4 million tons from recycling, which means like 70-30, right? In terms of recycled, in terms of how much recycling contributes to usage of metals, which is not a lot. And that really is due to the fact that it's not so easy to recycle because of such vast applications. Yeah, so first things first, the zinc annual production is of course on the rise, and the consumption is of course on the rise with regards to most metals, except of course steel. Maybe every metal is on the rise, and steel is a very complicated case, but you could see EU dominates in terms of zinc production by and large. Okay, of course China is dominant in all metals, but EU has also a very solid base of production of zinc, and there are only few companies, I think handful of companies, which produce zinc, not a lot of let's say small scale production going on as far as I know. And the most important route, and I think this is a slide from Boliden, one of the most important companies in Europe, is what they call as the RLE route. Okay, I think, okay, this is particular to zinc, this flow sheet, but the RLE route is very common route for so many different applications. If you ask Umicore how they deal with, let's say, even some other types of aqueous waste, for instance, waste electrical electronics, they simply follow the RLE route there as well. So this is a common route which is used for other metals and other types of applications as well. It goes like this. In the primary production, first you have the zinc sulfide, the sphalerite ore, right? So you have the roasting process in which you oxidize the zinc sulfide to zinc oxide, and then you produce sulfur dioxide, at which point you kind of capture it and then you convert it into sulfuric acid. Take a good note here, the sulfuric acid will do a lot of role. So once you do that, once you have produced zinc oxide, it's easily leachable rather than zinc sulfide, which is why you oxidize it on the first place. So you leach it with sulfuric acid, you produce zinc sulfate. It's not, of course, as easy as it is because you have many different kinds of impurities, and I have to go to a separate lecture if I have to give an intro on what happens during primary production. But one thing that you should know in primary production, what's the most important thing that happens, is that of iron removal. Okay, you have two different ways to do it. So here you see the reaction after the leaching reaction. You have the zinc sulfide, which can also react with the Fe3+ that is present in the solution possibly. Then it can have of course the positive effect of zinc leaching, but also iron 2+ concentrating in the solution. So you have to remove iron one way or the other. So I have told you multiple different ways to remove iron. That's what I've been almost doing all my life in research. So it's basically, one way is the manganese dioxide oxidation process, which I have already explained. and also jarosite precipitation process, which is really relevant to zinc, which is also something that I have already explained in the previous lecture. Maybe we'll go a little bit into jarosite later, but you already know the jarosite precipitation process as well. And once you sort of do that, other things take care of itself. Okay, you have also the cementation thing that is going on. Some other base metals could be easily cemented because zinc is quite reactive. Okay, once you have done that and you have sort of the steps purification is complete, you go to electrowinning. And I have also explained to you already the fundamentals of electrowinning. This is why these things go very fast. So you know already the fundamentals of leaching, roasting, as well as the electrowinning. So what happens in electrowinning? Zinc gets deposited in the cathode. So that's the metal we are looking for. Okay, and of course the water gets oxidized to oxygen at the anode. But take a good note here. In the entire overall reaction, what's very important is that we produce sulfuric acid back, and this is something that I always have emphasized in my previous lecture during electrowinning as well. To get acid back through anodic reaction is paramount. That is something that you really have to focus on, because that is the acid that you get back into the leaching step. Okay, if in case you decide to be a recycling researcher in the future, this is a closed loop that you have to really think hard about, because this is the Boliden flow sheet, and simply you could see that the sulfur dioxide that is the harmful emission during the roasting is not going to waste. It's not treated as one of the disadvantages, but it is turned into our own advantage, because we convert it into sulfuric acid, we leach it, and then during electrowinning we capture it back, and then once you capture it back, you set it back to leaching, so the loop is closed. Okay, not perfectly, but the loop is almost closed. Why did I show primary production to you instead of just jumping into recycling? Because once you know this fundamental, every hydrometallurgical recycling process of zinc is a variant of this. It's really a variant of this. Okay, you might have different types of roasting: nitrate roasting, sulfuric acid roasting, chloride, chlorination, rather than chloride roasting, chlorination processes. And you will always have a set of purification process, and then you do electrowinning to recover the metal. You may have acidic, you may have alkaline, you may have ammonia, you may have organic acid. I have told almost everything here. Everything that's going to be done using hydrometallurgy is a variant of this. Difference exists in chemistry. There are specific reasons why we follow one step over the other, but this is the basic skeleton almost for all hydrometallurgical flow sheets and processes. Okay, so you could see that the old scrap really plays a lot of role here, because the galvanized steel to recycle from that is a lot easier. To do the dezincification is a lot easier than let's say gathering from the new scrap, which is the things that are in the processing phase. What are the processing phase, the use phase, we will see in the next slide. But as I told you in the first slide itself, when you have some things that's used in the pharma product, it's the EOL RR is not going to be great, because it's not going to be easy to recycle at all. Here it says that it is 45%. Okay, that's more of a projection than reality. In some places, yes, but overall in the world it's much lower. It's 30. It's increasing, but not to an extent which is satisfactory. Then also you could see the recycled content, that is already you know the definition. It's not really a lot. It's just 25%. Okay, so what are the sources of secondary zinc? It's a lot of different sources exist. So you have the non-ferrous metals production processes, right here. So many non-ferrous metals, and all of their ores, one way or the other, has some zinc alloy, sulfide, silicates, whatnot, some alloy. So which means they are always going to end up in sludges and tailings. Is it worth to recycle that? It's really a tough question. Sometimes it's economically hard to justify. Sometimes it's environmentally really problematic, because you have the acidification and alkalization process going on. The alkalization simply means that when you just dump it into soil, I think you may or may not know about a problem of acid mine drainage. Basically, you could have acidification processes going on, which means that the water that is present in a particular geographical location turns acidic, and that can contribute to so many different tangential issues. So you need to be very wary of that. So okay, sludges and tailings, then dross and waste from hot dip galvanizing process, one of the most important sources. We will cover it in the lecture. And then you have also the zinc primary residue, which means the things that are produced during the primary production, and you have the residues from brass smelting, and you also have the dust from the electric arc furnace process, which is the recycling process for steel. We will have explanation towards that in the lecture. Then you also have the dust from copper industries and from also lead metallurgy, which also has some interesting specificities to it. We'll cover it briefly. And the zinc smelting waste, the primary smelting waste itself, is really a hazardous solid waste, and that has to be dealt with as well, because it has usually a lot of it. Look, this is a key issue here with zinc, is that to not beat around the bush, a lot of it is landmined, a lot of it just goes unrecycled, because of course the chemistry is complex. Of course, people haven't taken an environmentally conscious route towards it. It is bound to change maybe in the future, but it is what it is. So you have a substantial reduction in terms of energy consumptions and emissions when you do recycling rather than primary production. As I said, with all the metals, 25% is almost the accurate number here. And as I told you, the accumulation of slags, accumulation of tailings contributes to acidifying. So to the left, you could see the different types of wastes and the content of zinc, and then the classification and what are the problems. So yeah, all of them have their very specific problem. This was an article from hydrometallurgy. They talk from the perspective of hydrometallurgy. So you could see that one of the problems they say is that you have to remove iron prior to electrowinning. So that's one problem. And then there is also sometimes the formation of what's called as franklinite. You have the zinc Fe2O4. That's something that's tough to leach. And when you have formation of that or existence of that in your residue, it's not so easy to leach, simply because of the complexity in how the crystal structure is. And you also have, let's say, the existence of halides, especially from the smelter furnace fumes. The halides could create a problem in both solvent extraction and electrowinning. And yeah, so basically the key thing that you have to understand from here is that the EAF dust and the dross are two of the most important resources. And yeah, zinc accumulation of slag landfilling has environmental issues associated with it, which means it's imperative to recycle it, at least from the ecological perspective. Okay, so let's get into the first process for recycling zinc. This is the zinc oxide production from the drosses. So there are two possibilities: indirect or the direct process, the French or the American process, which is otherwise called. Basically, they both are one and the same when it comes to chemistry, except for the American process, it can handle a bit more complex feed. All of them recycle majorly the galvanization drosses, the drosses from the galvanizing process. And it boils down to this, very literally. Zinc has a very low boiling point, and it can be vaporized at 907 degrees Celsius. Most of the zinc recycling process exploit this phenomenon. So whatever waste you provide them with in whichever form, what they would essentially do is that you have the possibility to heat it up to a really high temperature, at which point you have the metallic zinc being vaporized, and then you can sort of collect it in the in one zone. So you see that one of the typical examples is the usage of this muffle furnace, where you have essentially two chambers separated by a sort of an arch. you have the charge going in, and then you have the charge heating up when you have a molten metal bath in which, and then you have the vapor zone. And once you have produced a vapor, what happens is that the zinc vapor travels into what could be called as a combustion zone. Okay, so the zinc combines with the air and then it forms zinc oxide. It's as simple as that. And then you collect the zinc oxide as in one chamber or the other. So it literally boils down to this very simple chemistry. And then you have some intricacies. For instance, the excess air also acts as a transportation medium, and then which helps the collection of zinc oxide, improving the efficiency. Also, you have the fact that this burning sort of luminescent exothermic reaction really helps the heat balance of the furnace, because then you have an exothermic reaction, you don't really need to heat up a lot. So this is the first way to produce zinc oxide from the process. Then let's go to one another type of furnace. Essentially, the chemistry is really the same, except the furnace construction is a bit different. In the Larvik furnace, what you have essentially is that three different zones: the melting, vaporization, and the separation zone. The difference between the Muffle furnace and Larvik furnace is this: you can have different kind of impurities, different types of impurities can be handled in a Larvik's furnace and not in a Muffle's furnace. How do they achieve this feat? By simply having two different taps, a lead tap and an iron tap. So what do they do? It's essentially quite simple. You put a charge and then you have electrodes, you heat it up, and then you have the condensed zinc and lead flowing in one direction and the zinc vapors flows in the other direction. Then of course it can go to the combustion chamber, which I explained before, can combine with oxygen, form zinc oxide, very simple reaction. Or it can be just condensed and then collected as zinc dust. Quite easy. The zinc recovery is taken care of here. Then you have the possibility that the lead goes here and then it can be condensed and collected here at one end. Or what they do also is that you have a different melting temperature set here at around 1250, because lead and zinc melts at quite low temperatures. But they have a different temperature set to here, and then they add phosphorus. Then they sort of form a V8 alloy, which can be melted and tapped at this particular junction. So you have the iron tap. So that's the only trick that is being played here. And other than that, it is quite literally the same as, let's say, the Muffle furnace in terms of chemistry. But even here, I have to say that if you throw in a waste with aluminum, it's not so easy to handle, because you have formation of really complex ferro-aluminum alloy, and that's not going to melt, that's going to go everywhere, and that's not going to be easy to be processed in the Larvik's furnace. Okay, so let's go on to the next part, which is a really important one, the electric arc furnace dust. Okay, so most of the processes that we are going to talk about today is in and around EAF dust. Okay, traditionally it's processed using what's called as a Wahl-Skin or a Wahl's process. And you see in this end what is the composition of the EAF dust and also the other types of dust and how much of zinc and lead and everything else is there. But just in case, to remind you again, the EAF process, you have the steel recycling in EAF, and then due to the fuming reactions of metals, you have all these sorts of zinc, lead, cadmium and all these metals getting collected at one point, or even there the vaporization can happen and then zinc can end up in dusts and so on. So these are the ways in which zinc is being collected from the EAF dust. And then you have, let's say, significant amount of zinc. You have to deal with it in one way or the other. Even to this day, I think a lot of EAF dust is landfilled or just dumped, and it is an environmental concern. So there are ways to process it, but not all of it, let's say, ends up getting recycled. For let's say, for every ton of steel, around 20 kilogram of this dust is being produced, and it amounts to 10 million ton per annum, which is not very low. And when you do this Wahl's process, what you have is the composition of the end product is indicated here. So this is the Wahl's slag, and then of course you have a slagging process, the pyrometallurgical process, and this is the main oxide you get from the Wahl's process, okay? Then they also have what's called as leached Wahl's oxide. So the only difference you see here is the reduction of fluorine content. So they just have a washing process to remove the halogen. Herein, I already gave away the most important bottleneck in handling EAF dust and the need to go beyond Wahl's process, because to handle halogens is not so easy, because eventually you have to fight with zinc, because all these things are also going to end up in dust or fines or in these vaporization chambers in one way or the other. Of course, you can sequentially try to remove it, and even if it ends up in the dust or the end product of an oxide, you can try to wash it off, but the presence of halogen is an impediment to this sort of pyrometallurgical process, and we will see how we can tackle it. Okay, let's get into the nitty-gritties of the Wahl's process. It happens in a Wahl's kiln, and the first step is pelletization of the feed. So you have input of your charge, and then the reducing agent, which is of course coke, and then you have all these slag forming additives. So the first thing that happens in the reduction zone. Okay, so you have zinc oxide or all the components that is present in the charge in the waste getting into contact through the Boudouard reaction. So you have the carbon dioxide that is in the chamber, right? And then the Boudouard reaction is basically carbon dioxide combining with carbon to produce carbon monoxide. It's one of the most important reactions in pyrometallurgy, and I taught you in Ellingham diagram series when I taught you that lecture. So once you have that, that's almost the rest is taken care of. The zinc oxide can react with the carbon monoxide, forming zinc, right? So with the temperature set, basically what you can do is that sort of the temperature is set around 1250 degrees Celsius, right? So it's not a lot of other metals are going to be melted. So you have some formation of some metals, zinc, lead, I think silver, cadmium, and all these things can be formed. And then once you have done that, then you take it to a combustion chamber or the oxidation chamber, where you have the formation of zinc oxide, right? And then you can regenerate the CO2 and then it can be used back again. So the selective vaporization, which is preceded, which is the first step is the reduction, the following step is the selective vaporization here, okay? And the key problem here that they have faced is that it's a very simple process. It's an effective process, except the fact it's a bit energy consuming. And of course, in reality, a lot of it is fueled by coal. But barring that, it's a very effective and efficient process, and it's quite selective as well, because you essentially, again, vaporize and then collect it in the oxidation zone, right? But then the problem that they have found is that still you have with these the Wahl's oxide, which I showed you in the last slide, you have the Wahl's oxide can be straight away used in so many different applications, but the point is that you still have halogen present. So, and they had to deal with it, and then they did few things there. They could do sort of carbonate washing, or they tried to use other kind of wash to remove the halogens, and it did work, but then that's an additional step, and that wasn't very easy for them, given that it is a pyrometallurgical plant and then you have to combine often with it, and it's not so effective either. So that is why, and because of the fact that Wahl's process also has this limitation where you have to have at least 18% of zinc in the input feed. I think that's the number, 18%. Here's the key issue here. EAF dust also is very diverse. Sometimes you have maybe less zinc, then you have to play around with your dust so that it fits in Wahl's kiln. And imagine that you have some other type of waste that you want to handle, where the zinc is simply not 18%. Zinc is probably less. Probably other type of impurities are there, more halogens, and it's not so easy. This is why the necessity of hydrometallurgical process for zinc came up. And some of the processes that I'm going to show are very interesting. I'll tell you how in the later slides. So let's go. The first thing that I'm going to show you is a very simple Amex developed process by hydrometallurgy. Basically, what they do is a two-step leaching. So and in both the stages are connected in a countercurrent fashion. So the things flow in opposite directions. What they do is that first they do atmospheric leaching, okay, and then once they do atmospheric leaching, you have the presence of iron and all these things from the waste goes into the solution, and they do a pressure leaching step. And the pressure leaching step basically is done inside an autoclave at 200 and odd degrees Celsius. What happens is that iron gets converted into hematite and inside an autoclave, not a goethite, not a lepidocrosite. Those are hydroxides. Okay, you can deal with it, but hematite is much better. It can be used straight away in other processes. It's very easy to filter out. It's quite nice. So they managed to wash away the impurities. It's a hydrometallurgical step, and of course you have generic solid liquid separation step here. You could use solvent extraction, you could use other type of processes, and then probably probably electrowinning, and then get the acid zinc sulfate back. Okay, and that's it. It's a quite simple leaching process. That's about it. The next three variants that I'm going to show are quite interesting because I'm going to show you the Indutech Azinex process, Indutech Azinex process. This is, as far as the literature says, or as far as I know, probably the only commercialized process, hydrometallurgical commercialized process, at least in EU. And it was developed in 1990s, and it was piloted around 2000s, I think, and then it's in operation. I think they produce 2,000 tons per annum, if I'm not wrong, and it's very interesting. So the first thing is that the Indutech process produce crude zinc oxide. It's a thermal plant, and I think the reactions are the same. So you have vaporization, conversion, combustion into zinc oxide. That's not so interesting. That's already something you know. And then you have the hydrometallurgical plant, the Azinex process that was invented. So the thing that they were dealing with is that you have the way to do sulfuric acid leaching, right? So that's one way. But it's also possible to do chloride leaching, and it was shown to be quite effective in recovering zinc. But they had an issue there, so they couldn't use it for electrowinning. And I will tell you how they solved it. They solved it by two different ways, and both are very interesting. So the first thing they did was they took the CZO, or the things that is obtained from the Indutech process. They leached it with ammonium chloride and sodium chloride leach, right? So the first thing that you need to notice is the pH of these things. It's going to be around 6 to 7. It's going to be buffering around 6 to 7. Okay, so then the zinc goes into the solution as like this. It goes into the solution as an ammoniacal complex. It doesn't simply go into the solution as zinc chloride. It goes into the solution as ammoniacal complex, right? Then you have this complex residue, and this residue is not so easy to leach this thing because of how crystallographically tough this thing is. So they just feed it back to the CZO thermal plant, and then they try to deal with it. Okay, and then you have the impurity removal step. And you already know how to remove impurities by cementation. You use metallic zinc goes into the solution, the other base metals can be cemented out, especially lead, cadmium, etc., and all these things. So that's the impurity removal step. That's not the interesting step. So then what is the interesting step? Here we go. So the one thing that they tried here is that they were struggling with the fact that, you have, when you use chlorides, you have instead of oxygen evolution in the anode, you have chlorine evolution in the anode, right? And once you have chlorine evolution, it's not so bad, but the thing is that some chloralkali plants can handle that. But in reality, for recycling plants to handle chlorine evolution is difficult because the anode lifetime will decrease. It's a very intense process, and it's not so easy to have a stable anode over a long period of time. Then you have to opt for a very expensive anode, and that's a problem altogether. So they had to solve this issue, and then they came up with two different solutions. One solution for Azinex was this. They took the leach solution and they had it in the catalytic chamber, and then they used a cation exchange membrane, and they had an electrochemical reactor with 2 chambers, and instead of chlorine evolution in the analytic compartment, they just filled it with sulfuric acid, and then they let oxygen evolve from sulfuric acid. That's a really nice solution. How did chlorine not migrate to the anode side? How did not chlorine evolution happen? 2 things. First, the chlorides were stopped by using a cation exchange membrane. In a cation exchange membrane, only cations can go through. Chloride is an anion. Okay. Second step, what they did was also fill the other compartment with a non-chloride solvent or a solution. They use sulfuric acid. Easy to produce oxygen from there. You have a chamber in between in which you try to avoid the migration of the anions by just putting a selective membrane, and you fill up the other compartment with a non-chloride solution so that you just let the oxygen to evolve. So you don't need to worry about chlorine evolution. That's one way they solved it. Okay, but this is altogether another way that they actually found, and it's very nice that they actually found it. I'll explain to you why. So the issue is that they took this and then they said, okay, we are producing ammoniacal solutions, right? So you are telling me that chlorine is going to evolve in the anode, and then they were like, so what? They took the chlorine gas that is evolved, and then they know that, of course, you have the ammonia in the solution, and that's going to combine, and the combination is going to just give you the hydrochloric acid back, and then also just the nitrogen gas is going to evolve. So that's something that's really fascinating. So because they did have chlorine evolution, but they tackled it because of the fact that it is essentially an ammoniacal solution, and it's useful to have an ammoniacal complex because this is going to be stripped away anyways when you do cathodic deposition, right? This is the cathodic deposition step. So you have the zinc ammoniacal chloride complex combining with the electrons to produce zinc and ammonia and chlorine. And this ammonia is basically going to take care of the chlorine gas that's evolving and then form hydrochloric acid. So that's really, really nice. And as I told you, they have to also deal with the fact that they have other sort of impurities inside their solution. I think they have to deal with calcium or magnesium impurities, and then they had to do a washing step. So here they did this washing step of sodium carbonate or a bicarbonate wash, and then they tried to take care of these calcium or magnesium by just precipitating them as carbonate. That's one way they actually dealt with. So okay, 2 different stuffs, 2 different processes, very interesting chemistry, completely commercialized and then still working, and it's very recent, a novel that they tried to install it now. So the good thing is that you could handle halogens here. You see halogens are inside the cell, they are handling it instead of the pyrometallurgical process. The second good thing here is that they could also not worry too much about the presence of so many impurity metals inside the solution. They have one way or the other to do precipitation. So that's the advantage of this particular hydrometallurgical commercialized process. Okay, so one of the most, let's say, interesting flow sheets that I found is the solvometallurgical flow sheet in the 1980s. Basically, solvometallurgy is a novel field which is gaining a lot of interest, and I'll have really a mini lecture on solvometallurgy for you guys to learn about it. But it is not something that's really new. It also has existed in different formats, and this is a paper from 1980s. And the whole hydrometallurgical recycling of EAF dust was summarized by Professor Binamans in a review in 2020. It's one of the hot articles, and I will post it in the UV, and I recommend you to at least read the EAF part, because the focus was on the hydrometallurgical way of handling all the wastes, different sort of streams from steel production. But I would recommend you to just focus on EAF, because there is so many processes and there is so much to learn. I specifically took this process because this showcases the use of solvometallurgy in 1980s, and it showcases how interestingly they came up with a solution. So the first thing is everybody knew that the chlorides were a problem, and then they had to solve it. Basically, the vasatic acid provided a way. The organic solvent can be, so you can sort of leach everything into the organic solvent, right? So you have the vasatic acid, and then the zinc oxide goes, and then it takes into zinc versatate or whatnot. And the halides, whichever is going inside, the impurities that's present, it's basically can be scrubbed with water from the organic solvent. So that's one good way, okay? And of course, you can strip through, let's say, putting an acid into this complex organic, and the zinc will go into the inorganic phase, and you will get the carboxylic acid back. Do you see how it works? You have two immiscible phases, right? You have the zinc versatate in the organic phase. You bring it into contact with sulfuric acid, an inorganic phase, okay? The zinc from the organic phase can come into the inorganic phase, and you get the acid back, the carboxylic acid back. That's pretty much the principle of solvent extraction as well. So that's, or like at least the stripping part of it. So that's one way, okay? Then they had to also deal with iron. So that's something that they came up quite interesting as well. So they took the iron containing zinc sulfate solution, okay, it's pretty much a simple inorganic solution, and they brought into contact the organic with it, the carboxylic that we are talking about here. What happened was the iron versatate and zinc exchange. So you could take one to the inorganic phase and the other to the organic phase. And this was quite novel because you have efficient separation of iron and zinc as well. So they solved multiple problems by using vasatic acid, and they could continue with the normal line of doing electrolysis from a zinc sulfate solution, in which you have oxygen evolution in the anode, zinc deposition in the cathode, all these things happen. So this is, let's say, an interesting flow sheet in 1980s, which involved an organic acid leach, which wasn't very common, at least, okay, commercially not common in those times. Now we have a lot of investigation. Okay, and this is a graph from the article that I was talking about. Somebody who had a lot of time in their hand took the EAF waste, took all these solutions, and then they leached it with different concentrations, and then they wanted to find how much is zinc going in, how much is iron going in. It's your major impurity, how much is iron going in, and how are things faring. Some poor graduate student had to encounter so many solutions, and then they had to do the leaching. But we have interesting results from that anyways. So what they found is that the aqua regia, the particular concentration of hydrochloric acid and citric acid, they had the highest of zinc and the lowest of iron. And then the key thing is that, okay, citric acid is a bit, let's say, benign, but it can't dissolve the zinc ZnFe2O4, again the same issue. And then they found that if you have lead in the stream, acetic acid can do enhanced extraction as well. There is a specific reason to it, but it's too detailed to go into. Okay, anyways, so the other thing that I wanted to talk about is that somebody also tried with this crazy looking ammoniacal iron sulfate and used it to leach. And they had an interesting result actually. So what they found was when you take this, basically this thing is pretty much an alkaline thing, or at least in the neutral pH, let's say, not really alkaline, but not acidic at all. I think 8 to 9 pH. So they found that you have to heat it up. I think they heated up to 80, 90 degrees Celsius. And one thing you have to actually know is that the iron oxidation is very sensitive to temperature and pH. If you have a really low pH solution, it's very difficult to oxidize the iron. If you have a high pH solution, it's high pH in a sense after 7, 8, it oxidizes very fast. So by its own crystal water, you have the oxidation of the this complex into Fe3. And then, as I have indicated to you before, this can release the protons. Once you have this release of protons, that can be used to leach the zinc from the EAF test into the solution. Okay? But that's not the interesting thing. That's something that's known. But this also, if you notice correctly, resembles a little bit of the jarosite. Okay, so simultaneously they also form jarosite, and then the process became a jarosite process. So it's basically how they came up with this is not they didn't solve the problem by starting with the leachant. They actually looked at, let's form jarosite. Okay, and what could be the thing that can give me jarosite at the end of the process and also zinc into the solution? And then they asked the question in reverse, and then they formulated the leachant in the first place. So these are the interesting details that you get from the paper. So to end up, I will show two other sources. One is from lead slags generated in lead metallurgy, and another is an interesting source. So the lead metallurgical slag is very simple. It's basically the same. Zinc ends up in slag in lead metallurgy because it's zinc oxide, and then they try to keep conditions in such a way that lead forms as a metal and zinc goes into the slag as oxide. And you take this oxide and then you put it inside a furnace, heat it up to 1200 degrees Celsius, and then you have the charge together with the CO2, and then you have the Bourod reaction, and everything is the same. You have the formation of zinc, and then the zinc vaporizes, gets oxidized, goes into zinc oxide. You can also recover lead oxide from this slag in a different manner, but everything else is pretty much exactly the same. So first you have the reduction reaction, and then you have the zinc vapor escaping, and then combustion, and then formation of zinc oxide. So that's one thing. They also, it's not done in a Wales kiln or something. They do it in a separate type of furnace, but the principle remains almost the same. So here's the last slide for the day. It's about jarosite leaching. So if you know already the primary production process that I taught you in one of the first slides, you have the iron removal happening as a jarosite. So I think I have already told you how jarosite precipitation happens in a previous lecture when we talked about precipitation. Okay, but the jarosite is also a source, a secondary resource from which you can recover zinc and lead. And it's very interesting because you have a lot of jarosite precipitation processes from so many industries, and now jarosites are again and again stored in dams, or like they are dumped, and it's creating landfill issues, it's creating environmental problems. So jarosite has to be taken care of as well. And there are many ways to recover things from jarosite, but I decided to show you let's say a novel variant using methane sulfonic acid. Methane sulfonic acid is an interesting alternative to the normal inorganic acid in terms of leaching. It's really a strong acid. It's not at all toxic. It has very low toxicity, and it's comparable to inorganic acids in its strength. So, and it's very useful and suitable electrochemically. You can easily have deposition reactions from it. So why don't people often use it? The cost, it's not so cheap. But it has interesting chemistries, and you can learn a lot of interesting things from it. But even the cost can be offset in one way. I will tell you how the cost can be offset. If you're, let's say, very careful enough, it can be offset. So this is a paper from Clifton Paulden, and it was done in 2019, 2020. They took the jarosite, they had the solvometallurgical leaching, which is essentially leaching with methane sulfonic acid, and what they found was that lead was really soluble. Lead from the waste immediately went into the solution, whereas it wasn't as much of zinc or iron going into the solution. Iron was pretty much completely going into the precipitate, because with increase in concentration of the acid, that is, if you reduce the amount of water, what they found was that they could precipitate one metal over the other. So the iron, most of it went into the precipitate. Zinc, half of it went into the precipitate, half of it ended up in solution. The most interesting thing happens here. So you take the precipitate, you take the leachate, which is almost all of the lead present in the waste has been dissolved selectively, and 50% of zinc, and almost nothing in terms of iron. You take the leachate, and you can have a sort of vacuum distillation process in which you can have the methane sulfonic acid recovered back from this leachate. So the methane sulfonic acid neatly goes back. You can't do it for so many inorganic acids. Okay. Once you do that, you form sort of a collective precipitate, and this precipitate can be processed further. So essentially, this is a very interesting process because of all the important attributes of MSA, methyl sulfonic acid, but also the fact that you can indeed capture the acid back and then send it through a simple vacuum distillation step. And that is the major advantage of the jarosite leaching through MSA. So they didn't go on with the route with electrochemistry because it could also be that some of it can be selectively deposited. They didn't proceed further. But yeah, it's an ongoing work, and you could see that coming maybe in next couple of years. Okay. Having said all these things, we wrap it up with zinc today. So I hope that you learned a lot from the zinc lecture, because this is a sort of gateway opening to us going a little bit deeper into hydrometallurgy. And as I said in the themes, we are going to do an interesting exercise. What we are going to do is that each one of us, including me, we are going to take at least 2 flow sheets for an end-of-life product. It can be also, you can take industrial wastes, residues, anything that you want. Take at least 2 flow sheets and explain what's happening in the flow sheet step by step. Focus on 2 things. Focus on how the flow sheet is constructed, and what are the key reactions, and what are the basis for separation. How are they valorizing the other things that are not actually recovered in the main line in the waste, from the waste, and how are they adhering to the principles of green chemistry? What are they doing? What are they lacking? So these are the things that you can come up with in terms of questioning. That's pretty much, that is all to it in recycling, to be honest. And once you have formulated that, let's choose a date. Let's present to each other what we have actually learned. And by this way, you learn a lot more, because you are forced to actually compare between flow sheets. You are forced to understand them before you are analyzing them critically. So it will be very, very nice for you. So that would be an important exercise, and I hope you guys turn up on the day where we have the mini symposium, mini seminar, and ask a lot of questions. So see you for the next lecture. It will be copper, and then we go to waste, electronic and electrical equipment recycling, and that's it. We are off to uncharted territories where we talk about solvometallurgy and a lot of other crazy stuff that's happening right now in recycling.